Hello everyone. This video is about the single phase fully controlled converter feeding RL load. This is a two quadrant converter wherein the output voltage can be positive or negative, but the output current is always positive. This diagram shows the two quadrants of operation of the converter where the output voltage can take both positive and negative value and the output current is always positive. This is the circuit diagram of the single phase full converter, which is in the bridge configuration. We have four thyristors T1, T2, T3, and T4. And the input to the bridge configuration is single phase AC voltage. The output RL is connected across the bridge configuration. Thyristors T1 and T2 are forward biased in the positive off cycle, and T3 and T4 are forward biased during the negative off cycle. When thyristors T1 and T2 are on, current flows from the source through T1 through RL load through T2 and back to the source. Hence V0, it is connected, hence the load is connected across the source, hence V0 is equal to Vs. When T3 and T4 are on, current flows from the source through T3 through RL load through T4 and back to the source. And here again, the load is connected across the Vs with the positive end of the load is connected to the lower side of the voltage source and the negative end of the load is connected to the upper side of the Vs. Since Vs is negative, having the negative of cycle, V0 will be equal to again Vm sine omega t. There are two modes of operation of the full converter fed RL load, continuous conduction mode and discontinuous conduction mode. Under each mode, we will be having again two different modes, rectification mode and inversion mode. In the continuous conduction mode, the output current is always greater than zero and the output current never reach zero value. The rectification mode happens when the firing angle alpha is less than 90 degree, during which the average output voltage is positive. The inversion mode will take place when the firing angle alpha is greater than 90 degree, and during that mode, the average output voltage is negative, and during this mode, the converter will behave like an inverter. Hence, it is also called as line commutated inverter. The waveforms for rectification mode are given here, that is for alpha less than 90 degree. The first waveform shows the input voltage waveform, and the second one shows the gate pulses for which are given to the thyristors T1 and T2. The third one shows the gate pulse given to T3 and T4. The fourth one shows the output voltage waveform. Fifth one shows the output current waveform, and this waveform shows the source current waveform. We have taken alpha less than 90 degree and we are triggering T1 and T2 at this place. When T1 and T2 are triggered, as we have already seen, the output voltage will follow the input voltage waveform. So from alpha to the next instant of triggering, that is pi plus alpha, at which T3 and T4 are triggered, the output voltage, it is equal to the input voltage waveform. So we can find here that for RL load, from alpha to pi, the output voltage is positive, and from pi to pi plus alpha, the output voltage is negative. But since we have taken alpha less than 90 degree, the average output voltage of this waveform, it is going to be positive, as because the positive side of the waveform is greater than the negative side of the waveform. At pi plus alpha, when T3 and T4 are triggered, the output voltage again will follow the input voltage waveform. That is, it follows V0 is equal to minus Vs. Since Vs is minus Vm sin omega t, the output voltage waveform again from pi plus alpha to 2 pi, it is equal to the positive voltage, and from 2 pi to 2 pi plus alpha, the output voltage is negative. This waveform is the current waveform. So when T1 and T2 are triggered, the output current rise from a non-zero value to a greater value, and then again at pi plus alpha, it reaches the same value as before. Again from pi plus alpha, the current waveform rises and it reaches a peak value at some place, and again it reaches the same initial value as before. This is the output current waveform. The source current waveform, we can see that when T1 and T2 are triggered, when T1 and T2 are in the on condition, the source current waveform is positive, and when T3 and T4 are in the on conditions, since the source voltage is negative during that time, the source current waveform flows in the reverse direction. Again, when T1 and T2 are triggered, the source current is positive. So we have drawn the waveforms for output voltage, output current, and the source current. Now the waveforms for inversion mode are given here. So here we have taken alpha, which is greater than 90 degree, and we are triggering T1 and T2 at this place at alpha. At pi plus alpha, we are triggering T3 and T4. The output voltage waveform is given in this graph, in which from alpha to pi plus alpha, the output voltage waveform exactly follows the input voltage waveform. From pi plus alpha to 2 pi plus alpha, the output voltage waveform will be the mirror image of the input voltage waveform. And from this waveform, we can say that the positive side of the waveform is lesser when compared to the negative side of the waveform. And because of this, the average output voltage will have a negative value. This waveform shows the output current waveform from alpha to pi plus alpha. When T1 and T2 are triggered, the current rise from a non-zero value and reaches the same value at pi plus alpha at which the T3 and T4 are triggered. Again, the current starts from this value and reaches a maximum at some place and reaches the same value at 2 pi plus alpha at which T1 and T2 are triggered again. And the source current waveform is shown here. And the source current will have positive value when T1 and T2 are in the on condition, and it will have negative value when T3 and T4 are in the conduction. Now we will derive the average output voltage of the converter. The average output voltage is given by 1 by 2 pi integration over 0 to 2 pi V0 d of omega t. Since there are two pulses per cycle, we can take 2 by 2 pi and we can integrate from alpha to pi plus alpha V0 d of omega t. So V0 from alpha to pi plus alpha is nothing but Vm sin omega t. If we integrate over alpha to pi plus alpha, we will get the average output voltage, which is equal to Vm by pi into cos alpha plus cos alpha, which is nothing but 2 Vm by pi into cos alpha. Alpha can take its value from 0. For alpha equal to 0, V0 is equal to 2 Vm by pi, which will be its maximum, positive maximum value. When alpha equal to pi by 2, V0 will be 0. And for alpha equal to pi, V0 will be equal to minus 2Vm by pi. The V0 can be plotted against alpha to get the control characteristics. So if we plot V0 against alpha, we will get the control characteristics like this. Now we will derive the RMS output voltage. The RMS output voltage V0 RMS is given by square root of 1 by 2 pi integration from 0 to 2 pi V0 square d omega t. Now since there are two pulses in cycle, we can rewrite this equation as within square root 2 by 2 pi integration from alpha to pi plus alpha V0 square d omega t. And we can substitute V0 as Vm sine omega t so that we can integrate Vm square sine square omega t. So if we integrate and after substituting the limits, we will be getting the final expression for V0 RMS as Vm by root of 2 pi square root of pi, which will be equal to Vm by root 2. So V0 RMS for continuous conduction mode will be equal to Vm by root 2, which is the RMS value of the sinusoidal waveform. So in this video, we have seen the operation of the single phase full converter feeding RL load in the continuous conduction mode. Thank you.